Okay, the next step in order to graph a function using the information we can get from derivatives is to talk about the first derivative test for local extrema. So we talked about absolute extrema, absolute max, absolute min, and we are going to focus in now on more localized maxes and mins. This helps us look at especially where curves turn around. We talked about peaks and valleys being points where we have critical points. We've also talked about how critical points occur when you have like a cusp, like you can see in this picture right here. And we also have other critical points that don't really tell us anything. But the first derivative test is going to help us talk about what is happening in our curve based on what the first derivative can inform us of. So let's do this. If your first derivative changes its sign from negative to positive at a particular point C, so C is your critical point, and imagine like we did the first derivative sign chart in the last video, we're going to do the same thing again. But now, if your sign chart changes from negative to positive, that means your function was decreasing and now it's increasing. If you go from decreasing to increasing at that critical point, what have you achieved? It decreased, increase. That point has to be a minimum. So we say that f has the local minimum at your critical point C. On the other hand, if f prime changes from positive to negative, so you're increasing and then you start decreasing, at that critical point, you must have a local maximum. If the derivative does not change sign at C, then f has no local extrema at C. Now we might find out something about that point using the second derivative, but we'll talk about that when we get to the second derivative test. So let's see how we can use this. First of all, in the graph here, I have some examples. Notice our function is increasing up until this point. At this point, apparently we have a horizontal tangent line, so we have a derivative of 0. So this is a critical point. But notice the function continues to increase. Now, this point here is important. We find out with the second derivative, he's called an inflection point. And we'll learn more about that later. But as far as increasing and decreasing, we increase and then we continue increasing. So he is not a maximum local max or a local min. The next critical point we have is this one right here. Notice we increase up to this point and then we decrease. So we increase, then we decrease, we must have a local max. Then we decrease to another critical point, and then we increase. So if you are decreasing and then increasing, you have a local min. Now all of these greater than zeros and less than zeros, remember this is what we talked about in the previous video. If your first derivative is positive, like here and here, we're increasing. If your first derivative is negative, you're decreasing. So the information we had in the last video is going to impact how we work out this video's information. Then we have a point here. This is a point where the derivative is undefined. Notice we're increasing and then decreasing, so that point, that critical point, is a local max. In this case, he's actually the absolute max. All right, again here, we're decreasing and decreasing again. So it was a critical point, but because it's decreasing on both sides, the derivative is negative on both sides, he's not a local max or a local min. All right, and you can also talk about the endpoints, but most of our problems will be involving an infinite domain. All right, let's try this one here. It says, consider the function, that looks like fun, find the critical points. How do we find critical points? Well, we got to find the derivative. Does that look like it's going to be fun to find the derivative? The way it's written, you would need to use what rule? Hopefully you're thinking product rule. You could. Maybe a little bit interesting. I'm not sure if it would be the best way. Personally, I would say the algebra to simplify this before we do a derivative is probably beneficial, but that is a personal preference. So if you want to try and do the product rule, go for it. Otherwise, if we do the algebra, remember x to the 1 would be x to the 3 over 3. So distribute x times x, we add the powers. So x to the 4/3 minus a 4 times x to the 1/3. I think that's easier to take the derivative of, so I'm going to go with that one. So 4/3 comes down, using the power rule here, 1 less would be 1/3 minus power times the 4, so 4/3 x to 1 less. So if I do minus 3 over 3 here, I would end up with negative 2/3 as my power. Now, I've warned you about this when we were working on derivatives. You're going to have to simplify this because we need to find the critical points. When do critical points happen? When the derivative equals 0 or is undefined. In its current format, this is kind of hard to find. So let's work this out and do some algebra to simplify what we're working with here. First of all, I see that there's 4/3 in common and an x in common. So we can take 4/3 out and we can take x to a power out. The question is what power? You always take the smallest exponent. So 1/3 and -2/3. Which one's smaller? -2/3. Okay, now when we do that, 4/3 is going to come out. That's gone. X to the 1/3. If I take out x to the -2/3, remember when you're factoring, you're dividing. So x to the 1/3 divided by x to the -2/3. We end up subtracting their exponents. So if we have a 1/3 and we subtract a -2/3, we end up with a 1, 3/3. So first term, we have an x to the 1 left, minus, we're taking everything out of the second term. It matches exactly what we're pulling out. So we have just a 1 as a placeholder. I'm not done yet. Before I evaluate this derivative, I need to get rid of my negative exponents. So let's write this as a fraction. The 4 is going to be on top. The 3 is going to be on the bottom, 4/3. The x to the 2/3 is going to come downstairs and have a positive exponent. X minus 1, he already has a positive exponent, so he stays upstairs. This is a much simpler form in order to determine what's going on in this derivative. So we want to know when this is equal to 0. Remember, a fraction equals 0 when the top equals 0. A fraction is undefined when the bottom equals 0. So this is the benefit of doing the extra algebra. Once you simplify, you're able to just focus on top and bottom, but you have to get rid of all the negative exponents first. Okay, so on top, we're going to equal 0 when x equals 1. On the bottom, we're going to equal 0 when x equals 0. What we have here are our critical points. So find the critical points, done. Part B, identify the open intervals on which f is increasing or decreasing. This is what we did in the last section. We're going to build a first derivative sign chart. So create a number line and put your x's in order. So we have two critical points, 0 and 1 in order. Remember, I like to put dotted lines to denote that this is, I know what these are. First derivative is 0 at these points because these are my critical points. I want to know what's happening in each of the other sections. So let's pick a point to the left, in the middle, and to the right. We're going to test and see what the derivative is doing there. Let's see, to the left of 0, we can pick -1. Don't pick crazy numbers if you don't have to. In between 0 and 1, well, we got to do a decimal, so let's try 0.5. And to the right, we'll try 2. When you're doing a first derivative sign chart, you plug your test points into your first derivative. So first derivative at -1, at 0.5, and at 2. Remember, all you want is the sign. You don't actually need the value, you just need the sign. Let me copy my first derivative over because I wrote all over him and I want to point out something interesting. You should always analyze your derivative before you start plugging in because all you need is the sign. For example, the 4 and the 3 are positive, so they don't affect the sign. You can ignore those pieces. They're just multiplying by the rest of it. This part here has an x squared and a third root. X squared, when you square a number, that is always going to be positive. And then when you take the cube root, he's still going to be positive. Because he is always positive, he will also not affect your sign. Very, very useful here. Always look for any pieces that have a square or an even power, because they'll be positive. On the top part, we have x minus 1. There's no square here, so this is the part that's going to determine what our sign is. So he is who we are going to focus on. Simplifies your problem dramatically if you can do this. If not, you just plug in the x value and work it out. All right, so if I plug -1 into x minus 1, all I need is my sign. -1 minus 1, still negative. Plug 0.5 into the parentheses. That's still negative. Plug 2 in. 2 minus 1, that's positive. Put your signs on your sign chart. So we have negative, negative, positive. bringing them over. Now we can interpret. Remember, a negative first derivative means your function is doing what? Decreasing. So you can draw the arrow. I like the arrow because it helps interpret into a graph, or you can write the word. And then another negative. So again, we're decreasing. A positive. So we are increasing. All right, so identify open intervals on which f is increasing and decreasing. So I've done that here. So from negative infinity to 0, we're decreasing. From 0 to 1, we're also decreasing. And then we're increasing from 1 to infinity. Now notice I left the 0 as a separate point. You can also put this together as long as you understand that there is a point at 0. That point at 0 does exist. If it was a vertical asymptote, we'll see that later, then you would have to leave the gap here. So just watch out in my lab, and they might want these put together, so negative infinity all the way to 1. It really depends on how they want the answer. I would accept either way. It's 2 separate or 1 together. Find the function's local extreme values. So this is where the first derivative test comes into play. So let's go back up to that. First derivative test. If your derivative changes signs, then you have a local extreme value. So let's go down here and see if we can do this in the sign chart. Are we changing signs at this first critical point? We're decreasing and then continuing to decrease. So this first critical point is not a local extreme. At the second critical point, at x equals 1, we're decreasing and then we start increasing. This is why I like the arrows. They really help. You go down and then you go up. So what does 1 have to be if it's at the bottom of this curve? This is a local minimum. So find the function's local extreme values. We have a min at x equals 1. What is the minimum value? You go back to the original function and plug in your x. So our original function was x to the 1/3 times, or what was it? Yeah, times x minus 4. So I just plugged in my x value. 1 to anything is still 1 times a negative 3. So we get a negative 3. And there you go. That is the local minimum value. And that's it, because the second critical point, we didn't change the sign of our derivative, so he is not a local min. We can also talk about a function's absolute extreme values. Now in this case, we can't use the extreme value theorem because we don't have a closed interval that we're focused on. We have an infinite interval. The domain is from negative infinity to positive infinity. But we can make some observations here. So your function is going to the left, it just goes up and up and up. And to the right, it goes up and up and up. So if we're going up forever, there's nowhere we turn around, you would have found a critical point. You just go up forever. What can we say about our extreme values? Well, if we go up forever, there is no absolute max. There's always a higher point. What about absolute minimum? Well, we don't go down forever. Now be careful, I say that even though we look like we're decreasing here and here a lot. But there's a point here. This point is defined. If you go back to your original function, you get a point. What is that point? So let's talk about absolute min. The absolute min, because our function goes up forever on the sides, it doesn't go down forever. There's no vertical asymptote where we would do that. The absolute min can occur at either one of the critical points. So we need to actually calculate the value at x equals 0 and x equals 1. Basically, I'm just going to show you that the local min at 1 is the absolute minimum. So f of 0, if you go back to the original function, that's 0. And we already did f at 1, that was negative 3. So not only is negative 3 your local min, he's actually your absolute min. Why don't you go to Desmos, punch this into your graphing calculator there, and look, make sure it's accurate. But you should see that this is the absolute minimum value the function achieves. So that's the first example. I'm going to stop the video here, and you pick up more examples in the next video.